events of nature and their interactions, which is nicely captured in this graphic. Now, the way particle physics goes at that is by building the vectors, as anyone does. And the vectors that particle physics has built are really, I think, triumphs in instrumentation. The size of these experiments, the complexity of these experiments are really unique, I think, in the field of science. So here's a picture of the Atlas experiment, just for the scale, this is a person. And the other experiment is, a CMS experiment, and it really just captures the imagination. It fascinates us, but it also captures the imagination of the public, because it actually does make the front cover of, popular magazines like Newsweek. Even though it does capture the imagination of the public, you also know, and we all know that, journalists often get it wrong. And just as a side note, even though this is here on the cover of Newsweek, there are two mistakes on the cover. The first one is, it says this is the picture of CMS, and it says that CMS is the biggest experiment. Actually, it's not the biggest. Atlas is the biggest. It's the heavier one of the two, but Atlas is the bigger one. And the other one, which is, I think, a big mistake, it says it's European, and it's not European, because the US has contributed more than 30% to both of these experiments, and has contributed significantly in actually the machine. But with these experiments, we try to get at the science, and for the last couple of years, the field has also made, I think, enormous strides in getting at the science. 2 years ago, both the Atlas and CMS experiments discovered the Higgs boson, and this is a picture of the Higgs decaying into two gammas. Then, the experiment at DIA in China has a reactor neutrino experiment, has measured one of the last remaining parameters in the BMNS matrix for the neutrino oscillation, to measure the angle sine squared theta 1 3, and measured it to be rather small. And then, as you all read, I'm sure, is that 2 weeks ago, the BICEP collaboration had the first evidence of actually inflation and gravitational waves by looking at the cosmic microwave background radiation. And they measured this parameter R. So here's the power spectrum as function of angular momentum. And this bullet here is the indication that R, which is the ratio of the tensor to scalar ratio, so really, the effect of gravitational waves is actually much larger than people had expected. So the question then is, to just put this in perspective, particle physics, of course, has not done this alone. It has relied tremendously on other science disciplines. But at the same time, particle physics has had a broad impact for other sciences and for society as a whole. So the question is, what are the key connections and the synergies between these tools, techniques, and technologies developed in particle physics and other disciplines? So what I would like to do is to look at these impacts, and go over them one by one. So what I would like to do is first look at the detector technology, then go into computing, accelerators, and then facilities. And then we'll conclude with what I view as some outstanding issues, and then especially what the opportunities are for all of us. So first, detector technologies. So this is a major area of connection of particle physics that has reached, I think, all the way from medical industry to actually imaging detectors. So one technology that I would like to highlight is the silicon technology. The silicon technology that high-energy physics started and brought it to such an unprecedented scale that we see now realized in these LHC experiments actually has its beginnings in industry. It is because industry developed, the lithography and the integrated circuits. Is that what, particle physics capitalized on and started to make these silicon detectors. So again, it had very humble beginnings. Here's a picture of 1987 of an experiment at Fermilab where the area of silicon here is about 25 square centimeters. That developed all the way to, current experiments where the area of silicon is more than 200 square meters. In parallel with that, what was developed is application-specific integrated circuits. So these are integrated circuits that read out these devices. Now, believe it or not, that this technology that lies at the basis of this has been applied in neurobiology. Because, it was, in some sense, the crossing of the path of a particle physicist and a biologist to try to understand the problem that the biologist faces. He said, he wanted to measure the nerve pulses at the end of a retina. And what they developed is exactly the same methodology that we use in silicon detectors, because you have, a battery of electrodes, you wire bond it, and you read it out with an application-specific integrated circuit. So you use exactly the same methodology, the same techniques, and the same readout circuitry that was developed for particle physics to study the eye. And what they discovered actually that there's a new functional time of the retinal output that was not known before they did this. The other area where particle physics has had a tremendous impact, and still has a tremendous impact, is medical imaging. So here in photon computed tomography, what you do is, it's much better than tomography with gamma scattering, is where you use photons. So you measure the direction of photons very precisely before the object, very precisely after the object, so you measure the scattering, and you measure the energy loss of the photon in a calorimeter behind it. So this photon computed tomography is being developed at the University of Santa Cruz, and what they use is, again, silicon detectors, silicon strip detectors, to measure the trajectory of particles, and then a calorimeter to measure the energy loss. And the readout of this is exactly the same readout that we used for the Glass 30 telescope that is up in space. The main difference between this application and the application in space is that if you want to do photon computed tomography, you have to read these out. You want to measure, 1 million protons per second to actually be able to image, a person very rapidly. Now, this technology, has migrated to nuclear physics. Even here at JLab, there is the JLab Class 12 experiment where part of the ASICs that were developed that are being used to read this out were developed at Fermilab, and also at Phoenix. The SVT at Phoenix uses the readout that was developed at Fermilab for Run 2, and some of the assemblies actually occurred also at technology, and that is using what they call monolithic active pixel sensors. So in a monolithic active pixel sensor, what you do is you have a sensing medium, which is still silicon, but in the sensing medium, right on top, you also have the first stage of your front-end electronics. So you can do the processing, and you can put the logic and the intelligence right there where you do the measurement. Now, this technology was conceived by the particle physics community, but at the moment, it's the nuclear physics community, it's you guys, who are really running with it. So the first application of this technology is in the STAR Heavy Flavor Tracker, where they have a couple of layers of silicon detectors. And the further development of this technology could, again, really be very beneficial to particle physics. Again, to indicate you that the nuclear physics community is really pushing this technology very, very hard, this here is a picture of the ALICE inner tracker system, which is looking at the construction of a 7-layer tracker that will use 25 gigapixels. It's the largest pixel detector that has ever been built. Similarly for the experiment at GSI, where again the first 4 layers are going to be built with this technology, with the added requirement that it also has to be radiation hard, which is really something that the particle physics community will be very interested in. Now, the pixel technology, the silicon pixel technology, has also spun off into the X-ray community. So while the CMS pixel detector was being developed, and here's a picture of the CMS pixel detector, they realized actually that you could use the same technology to also measure X-rays. And the company was spun off called Vectris that has developed, these X-ray detectors, which are now the workhorses at almost any light source. Now, taking this even one step further, in Europe at the XFEL, there are a couple of X-ray detector projects that are being developed. The 3 are shown here. One is a hybrid pixel detector, the other one is a large pixel array, and the other one uses another technology that being out of the particle physics community. But again, these are all built as a collaboration between the particle physics community and the high energy physics community to enable their science. Now, integral to all of this technology is the readout. So as I mentioned already, application-specific integrated circuits were fully pushed by the particle physics community, and this is, I think, a rather interesting example of, the path that these technologies have followed. So in around 1999, the nuclear physics community actually needed a readout for the ALICE experiment at the LHC, and they developed a chip that was used for the pixel detector at ALICE. Then the project essentially stopped because there were no follow-on projects. But while working on the project for ALICE, they realized that this was a damn good chip to also use for X-rays. So out of this came the development of the ManyPix and the TimePix development that is now being used to make these X-ray images. Now it turns out that in these 10 years of development, and they really have pushed this development, now they have a chip, the TimePix 3, which almost meets all specifications for the upgrade of the LHCb detector. So it is not, the way I view this is, enlightened management that let this project go on and maybe have a little detour from its path has fully paid back, the investment that was made. And to show you here a picture, this is a picture that was taken by the TimePix, the ManyPix 3 chip, which shows the contrast that you achieve with this device. And these are 4 keV, gammas. And the only way you can get this, if you really have single photon efficiency and very, very low noise readout. If you compare this to the X-ray you get from your dentist, the difference is striking. I find it striking. Let me just change track here a little bit, and that is crystal development. So, we knew that BGO, which is this crystal, bismuth germanium oxide, existed in the 70s. But the L3 experiment at lab at CERN decided to actually at one point build an electromagnetic calorimeter using these crystals because it had the best energy resolution. And this is again something that is unique to particle physics, and that is the scale of these devices. So L3 needed about 11,000 of these crystals, and at the time that they wanted it, they could only go a crystal one at a time. But they contacted this Shanghai Institute of Ceramics, and they developed in conjunction with this company a method where they could build 36 crystals in one shot. And that simply was the breakthrough to make this technology available to the medical imaging industry, because then it suddenly became cost effective. So this opened the medical market, and 1,500 PET scanners have been built by GE Healthcare, using crystals grown by this method by the Shanghai Institute of Technology. Now another example is the development of ISO crystals. So during the last phase of the LHC, when CMS was building its electromagnetic calorimeter, they decided to use lead tungstate. One requirement for the LHC experiment is always that everything has to be radiation hard. So when they were looking at the radiation hardness of lead tungstate, what they discovered is a way to make lead tungstate radiation hard. That is through special annealing and yttrium doping. Now at that time, LSO was already discovered by Schlumberger, but somebody put these two together. So somebody, and he gives the particle physics community full credit for that, he says, that because of the yttrium doping, he, invented LISO. LISO stands for lutetium yttrium, silicon oxide. So that is the crystal that is now being used most within PET scanners in the medical industry. So here again, and now, in turn, the particle physics community can use these crystals for their next generation of experiments, because the MUV experiment at Fermilab would like to use LISO crystals for their calorimeter. Now, this this one I put in because it is the basis of the result from 2 weeks to look at gravitational waves. Because these gravitational waves have been detected with transition edge sensors. Transition edge sensors have been fully developed by the particle physics community. There's just no doubt about it. And what is a transition edge sensor? It's a little calorimeter also. So what you do is you have an absorber, and when a photon comes in, the temperature of this absorber increases slightly. And this absorber is a superconducting material. So what you do is you engineer the superconducting material to be right at the transition between superconducting and normal conducting, so that you're sensitive to the slightest change in temperature. So the slightest change in temperature gives you an increase in resistance, changes the current because it's voltage biased, and you read it out with a squid. And these devices are now, because they are phenomenally sensitive, they're being used in many different applications. Here I show 2 applications. The top plot shows this is the energy in keV, and these are the spectra. So this is what you would measure with sodium iodine all the way up to a transition edge sensor, and you can see that with the transition edge sensor you can distinguish all these individual peaks. Similarly for a biological application, because of their sensitivity. And they're also being used to really look at fundamental quantum mechanical processes, like looking at the Rosen-Einstein-Podolsky paradox. Now, some detectors that we use are, large area and relatively cheap, like these resistive plate chambers. So in resistive plate chambers, you have 2 plates filled with a gas, particle goes through, ionize it, you have an avalanche, and you read it out. Now, because again, the scale of the particle physics experiments are so large, you need these in large format, make them cheap, and how else can you use them? Well, the environmentalists have tried to use these to actually look at imaging, for example, an imaging of a dormant volcano in France, where they study, the interior of the volcano. So that was all I wanted to say about the vector technologies. And now I would like to move to computing, what particle physics has done in the area of computing. So first is particle physics is known for big data. But big data means something different these days than it did 10 years ago. So, Eric Schmidt, who is the CEO of Google, says that from the dawn of civilization until 2003, all the data that humankind generated, now we produce every 2 days, which is really true. But, particle physics is still recognized as the field that really pushes big data. So, as you all know, the World Wide Web was invented at CERN, and that was a response to the need, for scientific collaboration. The grid is a response to the need for increased data analysis power of all the data that comes out of these LHC experiments. So what you need for grid computing is really reliable high bandwidth networks and then access to these high compute power systems. So again, this shows you the problem that the LHC faced. Here is the event size in bytes versus the rate of these events. And this is where the LHC experiments live. And you can see that they're really pushing the rate and the size of these events. So then what the particle physics community did is they worked with the Energy Science Network, ESNet, to really develop a system that met the needs of particle physics. So this was really an interaction, a collaboration between the two, between the computing science group and particle physics to develop this. And based on that, the LHC also developed the worldwide LHC computing grid, and it was built on 2 backbones, the European Science Grid Infrastructure and the Open Science Grid in the United States. And again, the tools were all developed and for grid computing. And now grid computing is not limited anymore to particle physics, but there's a whole range of science disciplines that now for them it is the norm to carry out their analysis. Now I would like to give you a quiz later. This is a quiz on big data, and this is from Wired magazine from last year. The size of the circle represents the size of the data volume. The question to you is, which circle represents the LHC data? I'll give you the answer. This is the LHC data. You can see that Facebook, which didn't exist, and this is important, Facebook, which didn't exist when the LHC was proposed, it didn't exist 5-6 years ago, now just overwhelms everything with all the pictures of the dogs that get uploaded every day on Facebook. Another thing that I think iEnergy Physics can take credit for is the development of scientific Linux. It was actually developed at Fermilab and then later in collaboration at Fermilab and CERN. And now, it has a relatively small user community, but it does run on the International Space Station. And it is listed as one of the 20 innovations in the Chicago area that happened. By the way, some of the other inventions in Chicago are listed here. So it's interesting to see that it competes with the invention of the vacuum cleaner, for example. Then another thing, and this is where nuclear physics and particle physics have done together, I think, had a lot of impact, and that is the development of supercomputing through lattice QCD. So lattice QCD, at one point the theorists needed a way to tackle lattice QCD, and in the beginning the theorists tried to come up with a way to actually carry out these calculations. This, by the way, was Ken Wilson who started all this, and then in the 80s they actually began developing machines that were really aimed at the performance of lattice QCD calculations. So the initial effort there was really an effort, as I said, between the nuclear physics community and the particle physics community at Columbia, and that then grew, to the development of the first set of supercomputers, the Blue Gene supercomputers, developed by IBM. A few of the key people who were involved in this project from the start actually moved to IBM to develop supercomputing. And then, again, high-performance computing these days is being used in a broad range of applications, from studying climate change to looking at thermonuclear fusion. Another thing that many people may not be aware of is JANT4. I don't know how well it is used within the nuclear physics community, but JANT is a simulation package that has a very interesting set of tools to define the geometry and look for tracking. So you can define any medium that a particle goes through and look at the interactions that happen. And this, even though it was fully developed to simulate what comes out of the particle physics collision, has found enormous applications. These are all the projects in space where JANT4 has been used, and it's pretty significant. They're also being used for other, planetary missions. They're even being used now to study for DNA models. They look again for medical imaging, and even single event upsets are being studied with JANT. And another thing is that even Boeing uses it. Boeing is using it to look at the radiation dose for their flight crews, and actually there is a paper on it. Right? Even before I started the study myself, I was not aware of this paper, where it is interesting to see, that particle physics is actually trying to design an Airbus and look at what can be done in designing an Airbus to minimize the radiation effects on all of us when we fly and the crew that actually, the airline crew. Okay, then we come to accelerators. So accelerators, as you all know, is the workhorse for particle physics. At the moment, they are being used in a broad range of applications. So they're used to look at material science. Many discoveries are being driven by particle accelerators. And here again is a list of topics where accelerators are being used. So anyone, for example, who has an artificial hip for something, your hip has been treated with a particle accelerator because there's nitrogen ion implantation of the titanium here to make this a much better joint. Now, of course, there's also ion therapy, where again there's a huge overlap with nuclear physics. So these are the Bragg curves, the energy loss as function of the depth, in this case for water. And you can see that photons or X-rays have a rather broad spectrum of where they lose their energy. But we all know that photons, and especially carbon ions, have a very sharp peak in where they deposit their energy. So for specific tumors, ion therapy is really the most ideal therapy to treat certain forms of cancer. So this is a picture of the Heidelberg Ion Therapy Center in Heidelberg. And as you can see, it is very similar to, a particle physics or a nuclear physics facility, but it is being used to treat patients. Then we have superconducting RF, where actually nuclear physics is a major leader in that. So it's a major thrust for the next generation of particle accelerators. And this SRF is really driven by collaboration between nuclear physics, particle physics, material science, and chemistry. And again, it is exactly, I think, this type of collaboration with other science disciplines that really will drive this technology and this further, because we need the interaction with the material scientists to understand, where a cavity, for example, breaks down, or why you cannot reach the gradients that you actually want to achieve. Now, accelerators are used in industry almost everywhere, from disinfection of water to ion implantation for silicon devices to heat shrink films. Now, you all know also that we are starting to reach a limit with the scalability of accelerators. They're just becoming quite unaffordable. So one way to break that barrier is maybe through laser-driven acceleration. But, and this may really be required to enable us to make our next generation of particle colliders. But what this relies on is really advances in areas of science that are beyond particle physics. Because here you really need lasers, for example, that have kilowatt average power with terawatt or petawatt peak powers, with a large efficiency and with a high rep rate. So particle physics will become more and more dependent on these other technologies. The last topic is a few words about facilities. So we have HEP-operated facilities, so accelerator-based particle facilities. But one very nice example, for example, is the test beam at CERN was used for a cloud experiment. And the cloud experiment stands for Cosmics Leaving Outdoor Droplets. That is an experiment that is looking at the formation of aerosols and the formation of clouds using aerosol particles in the sky. So it's really an atmospheric study where they use particle physics facilities to actually get at that science. And the reason why particle physics can do that is they can provide them with particular beams that simulate cosmics, and they can provide the environments that they need. For example, the very ultra-high vacuum environments that we had for the beams, and in this particular case, in this huge vessel. One thing that is very appealing puzzling to me is the sharing of facilities already between the different disciplines. So here we have a particle physics experiment, the heavy photon experiment, that is, I think, a particle physics experiment, but it's taking place here in Home. At the same time, there is the experiment Sequest, which really looks at the composition of the C inside a proton, which is, falls under nuclear physics, which is actually taking place at Fermilab. And I really believe that we should have much more of that. Then we also have built facilities that are really built by particle physics. So we built, for example, the sky surveys. Fermilab built the dark energy camera, which is an array of about 60 or so CCDs to carry out these sky surveys to look at dark energies. It's built by high energy physics, but it really benefits a much broader community. And then, we have these huge infrastructures like SLAC and, Petra and DAISY that are being used as light sources, where,